So in example 5, we have to use induction again to show that this equality actually holds. So it's got the left-hand side with all the powers of 3. It's got the right-hand side with the fraction. And that's great. So that's what we're going to do. And I had started by saying let n be an integer, n is greater than or equal to 0. It's a good idea to say by induction. So if you don't do that, you may lose a point on a test. So even though you know it's going to be induction, I know it's going to be induction, please indicate that to me so I know what you were thinking, because in the next section we're going to be talking about proofs by strong induction, and they're a little bit different when it comes to the base case and the inductive hypothesis. So in any case, in the base case, we're going to grab the left-hand side and basically test out what it's equal to when n is equal to 0. So when n is equal to 0, we get basically 1 plus nothing, because 3 to the power of 0 is already equal to 1. So we stop right there, and that's the end. And that's pretty much the end of the left-hand side. And now we're going to test the right-hand side. And the right-hand side in this problem, it consists of the fraction 3 to the n plus 1, but n is supposed to be 0. So 0 plus 1 minus 1 over 2. Okay, again, I'm putting the 0 because n is supposed to be 0. And that's going to be 3 minus 1 over 2, which is 2 over 2, which is 1 at the end. And so it seems like the base case holds. So this is great. If the base case is not true, then there's no point in continuing the problem. Either we made a mistake or the theorem actually is not supposed to be true. But in this case, the base case holds. So we go on to the next step, which is the inductive hypothesis. So I'm going to go ahead and start setting it up. So what am I going to do in the inductive hypothesis? I'm going to basically assume that the statement that we're trying to show holds. So suppose or assume that the theorem is true for 1 plus 3 plus 3 squared plus so on and so forth, all the way to some random n that is equal to some random integer. So for some n equal to k. So in other terms, what I'm doing is I'm basically saying I'm assuming that this statement is actually true for one single number called k, and I want to prove that it's true for the next guy. So I want to show that the statement holds for the next integer. So I want to show that 1 plus 3 squared plus so on and so forth plus 3n plus the next guy 3n plus 1 is equal to 3, then n plus 2 minus 1 all divided by 2. So technically I should be writing k's in all these n's right here, but I don't, it's really not a big deal. As long as we kind of understand and we know what we're doing. We suppose that it was true for k, and we want to show that it's true for the next guy. So in some books they will change the letter, in some other books they don't. It just kind of depends on whether you can kind of understand what's going on or not. So regardless of what letter you decide to go with, that's what you want to show. So to do this, I'm gonna go ahead and start with the left-hand side. So now consider the left-hand side. So consider the left-hand side, which is 1 plus 3 squared plus so on and so forth, all the way to 3k and 3k plus 1. So I'm using k just to kind of show you a little variety. So just keep in mind that all of this right here is sort of similar to the 1 plus 3 squared, which was the inductive hypothesis. So that whole thing can now be replaced with the fraction 3 to the n plus 1 minus 1 all divided by 2. And we're left with the extra 3k plus 1 at the end. Okay, and so there we go. Let's get started. It seems like we have two fractions, and so maybe a good idea would be to put them both with the same denominator. So I'm going to go ahead and kind of like continue on the next page. This is the same thing as saying 3k plus 1 minus 1 all divided by 2 plus, well, let's see, we need a common denominator, so let's go ahead with the 2. So 2 times 3k plus 1. Since they both have the same denominator, we'll go ahead and combine it together, and it will say now 3k plus 1 minus 1 plus 2 of the 3k plus 1. Okay. Now, to do this, I'm just going to think of this as like a coin, and this is the same coin. So I have one of these coins at the beginning, and I have two of them at the end. So the total coin number is kind of like 3. And so 3 of the 3k plus 1 kind of coins. That's what I'm calling them. It's kind of reminding me of that coin problem that we did earlier. But, you know, it's not the same thing, but whatever. So, you know. Now, we have 3 times 3k plus 1. Since they both have the same base, we can use exponent rules. And the exponent rule that I'm going to use is basically the following one. It says if you have a to the n times a to the n, then you're supposed to combine them by addition. So I'm going to be going to use that right there. Okay, since I have the same base 3, I'm going to use the formula or the exponent rule to put the two things together and turn it into 3 to the power of k plus 2 minus 1 all divided by 2. Which, if I am remembering correctly, if I scroll back a little bit, this is exactly what I wanted to show. So that's the right hand side. It came out. So I'm going to go ahead and write right hand side, and which is what we wanted. And that's the end of the proof. And so by induction, so by induction, the problem is finished. QED.